Okay, whoever is out there, welcome to a hopefully quick demo of the newish TLA Debugger, a thing I've been working on for a couple of weeks now. I think it started at the end of last year, and then I got distracted, put out TLA Toolbox release, worked a little bit on the trace exploration, and then went into full gear again in January. So this is still work in progress. It's not done yet, and it's not integrated into the TLA Toolbox. It's integrated in Visual Studio Code. The motivation for the debugger is that even though TLA has this beautiful feature that you get error traces if a state violates a safety property, or if a behavior violates a liveness property, you get to see the trace, the values of all variables from the beginning of the computation until the end. But that's not good enough, I guess, I believe, if you write the behaviors part of your specification, where, for example, we don't know why a certain action is not enabled in a certain state, or another example is that you write a silly expression a plus 1 for which we don't know, for which TLC doesn't know the value, and then TLC crashes, and in the past you would have to, from its error message and sometimes an incomplete, a partial stack trace, figure out what's going on. At any rate, let's go into the demo, and for that we start with the place where you can grab the code. So I've forked Andrew Leguin's beautiful TLA VS Code extension, and with just a handful of commits enabled the debug adapter protocol, which is an extension of the language server protocol, which all originated in VS Code. And that's also the reason why I started with the VS Code extension and not the TLA Toolbox. There are plans to add this debugger to the TLA Toolbox later this year. So go to this release page here, grab the VS Code TLA 154 VSIX file, Visual Studio integration extension, something. I've done that already. And then you have to manually install this into your Visual Studio. So you go to extensions, and here mine has it already installed, 154. Yours probably shows 153, which is, as of today, the current released version. Here select the 154, reload, and then all looks the same if you open a TLA spec in the extension. This is not new, right? This looks the same as in the plain original extension, but we see it here. There is a breakpoint. We can add a breakpoint here and there. And we also see this check and debug model with the TLC button up here. So that's the only visible difference in addition to this check and debug model with TLC palette command. Click it, and then a few seconds later the VS Code extension starts TLC, connects to TLC, listening for debugger frontends for VS Code, and TLC is programmed to suspend the evaluation of the spec at the first assumption, if there is one, or at the first expression of the initial predicate. Since this spec here, which happens to be the Dijkstra termination detection algorithm in a ring with synchronous message delivery, aka EWD 840, has an assumption, it suspends here, and we get the familiar debugger controls: resume, step over, step into, step out, terminate, restart doesn't work yet. Get to see our breakpoints down here. There's a call stack, and this one just has one element. And in this variables view, there is a node called constants. So we get to see the value that color is defined to be. It's a set of white and black. And node, which is the set of naturals here, 0, 1, 2, because n, the constant that's declared in the specification in its config file, let's see here, is defined by the config to be 3. Okay, and then since this specification happens to refine the sync termination detection specification, it's an instance of sync termination detection, we also get to see the constants defined in sync termination detection, or TD in this spec here. Let's quickly switch over there. See, it has a node definition 0, 1, 2. So this happens to be the same here. The value happens to be the same set 0, 1, 2. It doesn't have to be. Okay, so far so good. Things seem to work. At the bottom here we see in the debug console TLC's output, parsing messages, and then we see that state space expiration starts, all nicely interleaved with these parsing markers here, which make the reading of the output a little bit inconvenient. But anyway, there's room for improvement. Okay, but now let's set a breakpoint. Let's say in the initial predicate here, and continue, and we see that TLC now halts, suspends evaluation at line 30. So initially evaluated line 29, and then went on to evaluate line 30. And we can see the value of the state, since this is a state level expression. So evaluated over the state, we see the value of active, which has already been evaluated, to the function from 0, 1, 2 to Boolean. And in this particular state, in this initial state, active equals this particular function here, false, false, false. And now we could step over color, resume, remove this breakpoint here, go to T color, and we see that the debugger updates the view to show the value of color, show the value of T-pos, and T color is still undefined yet. Its evaluation is pending, yeah, because this black here equals black has not been evaluated. As you can see, we can expand values, arbitrary nesting here, functions of sets, whatever, can expand arbitrarily down to atomic values. And hovering over the value tells you TLC's internal representation of this value. So this is a function record value, which is a function of the form D1 maps to E1 and yada yada dn maps to en. This one here, evaluation pending, we saw that before, and an int value. So TLC doesn't have naturals, even though this is a natural here in this spec. But that's an internal detail of TLC. And we see that the predicate, the name of the predicate that's currently being evaluated, for the initial predicate, it's always initial predicate and not the actual name. That's a shortcoming of TLC. Okay, so let's get rid of this breakpoint here, resume, and we see next it goes to type OK. So for the state we just defined through init, we now check the type OK invariant. We still see that the state, we, by looking at it, can see that this will check out, right? We could also step through it and this way figure out why this type OK is violated. But yeah, in this case, it's not violated. Let's see, I guess it changed it. Yeah, so I will add another breakpoint down here so that we also see that now, because we don't really, we're not in programming language, but doing state space exploration, we don't jump to inf after checking type OK, but we go back to TLC. Oh no, I get confused because it checks the invariant now. See if this is a thing with a live demo. So for this particular state, it now evaluates the invariant, the second disjunct here, P1 defined to be, there's just a J and so and so. The J has not been evaluated yet, but if we step into it, we also see that now J is assigned a value. And this time is 0 for the set here. We get to see the value of color. Color 0 is 1. Yeah. And this is checked to equal black, whatever that means in this spec here. Okay, let's remove this breakpoint. And I believe I removed the other ones as well. Let's see what kind of... So this one is a breakpoint that's obviously bogus. It's set on line 37 on a comment, which cannot possibly work. So that's why it's indicated to be bogus by a hollow breakpoint. Validated breakpoints show up as red dots. Those that cannot validate these hollow markers. Okay, so let's see. I have one more breakpoint up here that I don't care about. And now I have this breakpoint here in send message, and it looks kind of different because this is a hit count breakpoint. So this only fires if something is 2. Not sure what 2 is. Maybe the second time this unchanged is evaluated. No, in this particular case, in case of TLA plus, I made it so that hit count is 2 means for fire if the behavior, the prefix of the current behavior is 2 states long. So this should fire if there is initial state and then one successor state, and we are in the send message action. Let's see if it does. Whoops, no it doesn't, because as I said initially, the debugger can help us quickly figure out what's wrong with silly expressions. So I deliberately introduced the silly expression here, 0 plus a, whatever that means. We get this somewhat cryptic TLC message that for the operator plus overwritten in Java, so it's more efficient. It cannot cast the string value to int value. Well, those are once again where TLC internals show up, but it kind of gives us an idea of what's going on here, right? But if it's more involved, I mean, we also get to see the stack trace here. So contrary to plain TLC, which just terminates, and then you have to figure out from this partial stack trace that gets shown in the toolbox and the error trace, the top of the error trace and the topmost pane. Here you can expect the stack, go back and look at the values. So I have a visitor here in my room. So since nobody's watching anyway, doesn't matter. It's nice to occasionally have visitors. Okay, so there's something wrong with the spec here. Silly expression. We could introspect. We see that there's, in addition to the constants, there happens also to be the stack node here. What does stack mean? So it means in this evaluation stack, a previous point t color equals spec evaluated to true. So this is T color black equals true. That's this here that evaluated to true, so TLC didn't evaluate this disjunct here, and TPOS evaluated also to equals 0, evaluated also to true. And those, since they are from the perspective of TLC assignments, they don't show up as evaluations here on the stack node. They get shown here under the action node, where we see the value of the variables in the current state, and then also how they are defined in the next state, and the primed value of the variables. So let's make this larger. Active is false, 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 and the next state active is also false, false, false. Color is white, white, white. And since we are on line 45 before color is fully evaluated, its value is once again still pending, so hence the question mark. T color is black, T color prime is white, so it changed the color from black to white. T pos is 0, T pos 2 is 2, because this is n minus 1, and this is 3. Here's your 2, here's your white, here's your unchanged active, and this failed, so we have to correct this. Unfortunately, there is no hot code replacement yet. I would really like to implement hot code replacement and then resume state space exploration after fixing this expression, but Sunny doesn't, which is TLC's or the TLA plus parser doesn't support incremental parsing. So I'm afraid we have to start from the beginning. So once again, it stops at the first assumption, and if you don't like this, you can change the invocation of TLC to include no suspend, and then it will just immediately start to evaluate the initial and the next state relations of the behavior spec. Okay, so we've seen the exception breakpoints, which you can also turn off down here. We've seen regular breakpoints. Now let's see how this hit count works. If it works, yeah, it works. So this send message now suspends for behavior of length 2. We can't see this here. We just see that it's a send message, and because there has to be an initial state, that's how the behavior spec is defined, we would know it. But we also see this, let's make this smaller here, we also see the trace. So whenever a breakpoint for a state and an action level expression is hit, fires, we get to see the trace here from some initial state to the current state. So this happens to be the initial state in this behavior, and this happens to be the current state, partially evaluated, right? Because this unchanged here, T pos T color, has not been evaluated yet, which we can also see over here. T color and T pos, here shown as prime, have not been evaluated. But as you can see, this hit count is 2. And I think if I would make it hit count 3 to make it more interesting, then it will never hit, never fire, because this spec's diameter is just 2, it's so tiny. But it would also show up here. And the reason why it's in a separate node has just technical reasons. Ideally, this trace would show up in this call stack, and then we would have 2 granularities here in the call stack. Would see the predecessor state here, but we can't have subnodes and expand call stack items. That's why it's in the variables view right now. That's a limitation of this debug adapter protocol I mentioned earlier. 20 minutes. Okay, so let's terminate this and quickly head over to my notes. Evaluation, switch stack frames. I've shown you hover various nodes in the variables view, constances, stack value, state and action nodes, and the trace value, which took a considerable amount of work and time to show this trace here, because internally TLC is so highly optimized towards a efficient state space exploration. So it throws away all the information that you would want to see in a debugger, and I had to change parts of TLC to maintain this information without making the regular exhaustive state space exploration super slow. So as always with software under the covers, a lot of work went on. Okay, so let's move to a slightly more interesting specification, which happens to also be an extension of Dijkstra's termination. So this now is EWD 840, but with asynchronous message delivery, which is Zafra's version of termination detection in a ring. It's a little bit more involved, and most importantly, we have many levels of refinement here, and I have an animation. So this is an animation spec, and I think, let's see if this works. Yeah, so this is the animation I created earlier independently of the debugger, for which this NMTLA here is the specification. And this animation uses this alias feature that is new in TLC, and aliases are difficult to debug if your alias expression is bogus and TLC cannot evaluate it. It will simply fall back to printing the original state. But as I will show now, the debugger is actually quite useful to debug broken alias expressions. And also what I would like to show is how we can use this to debug a refinement mapping. So let's go to anim. So whatever is the currently active specification is the one that the debugger/TLC will check when we hit this button here. So I have to activate the editor, the anim editor, for the anim spec to be checked. Now, because there's only an assumption in the gen ID, it will stop at the gen ID, but as you can see here, so we are actually checking the animation spec, which we also see here, which is the last entry in this list. And as I said, it's a little bit more involved. So we have a hierarchy of refinement mappings here. Anim extends gen ID, which refines gen, which refines 998, which refines async termination detection. Once again, we can look at all the constants. The difference here, for example, is that between gen and gen ID, the refinement is such that gen ID defines node to not be a set of naturals, but a set of strings, addresses, whatever. And we see the differences here in the constant view. And the debugger also shows us the name of this instantiation in the spec and the name of the actual module. Okay, let's see. So once again, hover should work. Let's see who initiator here. Okay, so this is apparently not evaluated yet. Initiator A. Oh, so we were over the definition and we're not in the right scope yet. We are in the scope of the constant level assumption. That's why we don't get to see the hover for initiator. So let's just resume and see it hits the breakpoint here that's set on the refinement mapping, which is a little bit more involved than most straightforward refinement mappings. And we can also step through here. So now we step into this node to net function that maps the logical node names to these numbers in the high level spec. And yeah, we could just go through there, step into the various sub definitions, yada yada yada. So that's nice. Get to see the state for which the current refinement mapping is evaluated, and once again the trace. And then last step, let's see. So this still fires. Let's MCTLA. I don't know where this breakpoint is coming from, but it's gone now anyway. Let's clear this here. And let's clear this guy and let's remove this. So this should now, see, we're computing states, and oh yeah, mistake. So this animation is only interesting for longer behaviors of say 40 states or so, and doing exhaustive search for a trace length of 40 and above is just too expensive for this specification here. The toolbox's profiler would reveal all these bottlenecks. But what I wanted to show is that this debugger is integrated with the settings of the TLA Plus extension. So we set this to simulation and then debug it again. It errors out on us. Okay, so let's just try it again. Live demos. So perhaps this check model with TLC, stop node, unrecognized, option, simulation. So I guess there is a typo. Yeah, it's simulate, right? Working with this piece of software so long yet, I don't know. Actual wording of the parameters. Okay, so now it starts up again, but it also shows how you would debug this problem. So if there's a parsing error on your spec, the debugger doesn't really handle this well yet, it simply doesn't start. Make sure that your spec parses, and also if the debugger doesn't come up, make sure that without the debugger, just checking the spec works. And TLC starts. Okay, but now it's running in simulation mode, which we don't see here because this gets printed before the debugger captures the output. But yeah, so now what I wanted to show is we're now on this refinement mapping, in this alias expression here, with an expression breakpoint that's configured. Let's see, where do we see the expression? Enable, remove, edit condition. For some reason I can't, can only remove the breakpoint, but it's, as you can see from the icon here, it's a hit count breakpoint, and earlier I set hit count to 10, so that's why it halts after 10 states. We get to see the full trace here, and can now check and see how this alias expression gets evaluated for this pair of states 9, 10. Can resume, remove the breakpoint, and let TLC run to completion. So here we are, finished. It ran in simulation mode. That's why it was so fast and produced this trace of I don't know what length, non-trivial length, in a very 84 states, 85 states in a short amount of time. Okay, that's all I have for now. Again, if you wanna try it out yourself, go to the GitHub repo, Lemmy, VS Code, TLA Plus releases. Make sure to come back regularly because I update this here whenever I discover a bug, and just earlier I had to fix an issue with an incompatibility between Windows and Unix. Yeah, so if you have issues, report them here under the issues, but first check if there's a new snapshot release. Thanks.